Now that we have a bunch of vector spaces at our disposal, we can start applying the ideas of linear algebra from Euclidean spaces to these other vector spaces. And maybe the first tool that we came up with for Euclidean vector spaces is linear combinations. So if we have a vector space V, a linear combination of vectors is just some vector in that vector space that you can write as scalar multiples of the given vectors all added up for some scalars. Okay, so in particular, if we think about this vector space of 2 by 2 matrices, we could try to write this matrix 1 minus 2 3 minus 1 as a linear combination of these four matrices 1 0 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So how could we write our given matrix? Let's call this A, so we don't have to write it down again. How could we write this as a linear combination of these other four? Well, it's not hard to see how for this particular example, right? Since 1 only shows up in a single location in these other four matrices, the position of that 1 is just going to be the only way we can get non-zero entries in the corresponding position. So to get A as a linear combination of these four, we would need, let's see, to get this 1 to show up, we need 1 times 1 0 0 0. And then to get this minus 2 to show up, we'd need a minus 2 times 0 1 0 0. And then to get that 3 in the lower left to show up, we need plus 3 times 0 0 1 0 plus, and then to get this 1 to show up, this minus 1 to show up, I guess we need a minus 1 times 0 0 0 1. Okay, so this displays this matrix A as a linear combination of these four other matrices. You can see what's really happening here is that these four matrices, I mean, we could do this for any matrix on the left-hand side. So what's really happening here is that these four matrices span the vector space M22, right? In fact, they're a basis.